We've talked so far in our class about the way a point source of light generates an energy distribution when we are using a point source that's either continuous wave, CW, or when it's pulsed in time, a single pulse. That's called the time domain. This video, as you can read, is going to be about when we use a light source that operates in what we call the frequency domain. So in the frequency domain, you're going to have a source of light that is only at one location, a point source in this model, but it turns brighter and darker with time. And what we say is that it's being amplitude modulated. So this is an amplitude modulated source. And what does an amplitude modulated point source get modeled as? We're going to call that source S. It's a function of position and time. And we are going to model it using complex notation. So I'm going to write this as the real of something complex. And here's what it is. There's a certain power that the source has, and you'll see what I mean about that. It is changing with time, but we have to set a constant somewhere. So there's a certain amount of watts of power. And then we have it be 1 plus an oscillating term of amplitude A. So that's why I'm using the real part of a complex number, because I have some amplitude A. A is going to be less than or equal to 1, and it has a time varying component. And then that gives me the temporal dependence, and the spatial dependence on position is a delta function at location R, at the origin, in other words, when R equals 0. So P, again, is a power. The delta function has units of 1 over meters cubed. So I've got power per meters cubed, and the source has that same units of watts per meters cubed. So if I turn a light source brighter and darker in this way, it's sort of 1 plus a certain amount of a cosine, but never goes negative, we're going to get a certain energy distribution that is resulting from that. And that energy distribution is going to be U as a function of where I am in the tissue, some distance, what distance I am from the light source. And what we know is that if we sit here at location U and this light source is turning on and off with its intensity versus time, I am going to experience a time varying amount of light that's reaching me. So we can separate this into what we'll call, in the language of the book and of the field of biomedical optics, a direct current or a steady state term, which I'll call the DC term. So there's going to be some steady amount of light that's always present at U. And then there's going to be a time varying component. I'm going to not even bother writing the real of a complex number anymore and move right to just writing it as a complex number. So I'll just say there's an AC alternating current term, which is a function of position, but it also has a time dependence, e to the minus I omega t. Remember again that my notation here is that we're really taking the real of this entire expression, so this e to the minus I omega t becomes a sinusoidal oscillation. Fine, we now have the ability to plug into the time-dependent diffusion equation. I will remind you of what that is. It consists of 4 terms, and I'll order them in the following way. There's this diffusion coefficient, I'll write out what that is in a second, times the Laplacian of U. U is the total sum of the DC and AC term, minus a time derivative of U, minus an absorption-related term. Cn is the speed of light in a material refractive index n. And on the other side of the equation are any source terms that are driving it. And because of the way we've happened to choose our plus and minus signs on the left-hand side, we actually write the source as a negative number, negative source, like that. Let me just remind you that the diffusion coefficient in our textbook is written as the speed of light over 3 mu times mu s prime plus mu a. That can also be written as c over 3 times what we call mu total prime. That's just mu t prime is mu s prime plus mu a. Okay, we're going to insert this source and this u into this equation. And let's see what we get. We are going to be sticking in a udc and a uac into this overall equation, everywhere where you see a u. And I'm going to lead you by writing the CW or DC terms in red, and I'm going to write the frequency domain or time varying terms in green. So let's start figuring out what terms we get. So first we have the d del squared term. So that there's one for AC and DC. So I'll open a bracket here to say that we're going to create a CW grouping, and the CW first term is going to be positive d del squared UDC. For convenience, I'm not going to write the R dependence anymore since we have a lot of terms to write down. And I'm also going to open up a bracket for the frequency domain terms that we're going to have, and that's going to also be positive d del squared UAC. Now we're going to have at the other end of this equation, when they end, all of the terms that are time dependent will have an e to the minus I omega t in them, whether I'm plugging in for source or for u. So I'm going to take that e to the minus I omega t and bring it outside of the entire equation. There is no corresponding term for the CW terms. All right, let's plug into the next term. That's the minus time derivative term. So the time derivative of e to the minus I omega t brings down a minus I omega. We have a minus sign as well here. So this is going to give us a plus I omega UAC. Now what's interesting here is that the time derivative of the DC term is 0. So I don't write anything up here. So that's a difference between the CW and frequency domain terms. The third term in the diffusion equation is this absorption term. That's going to be the same for both of them. Minus mu a speed of light and u dc. And on the other one, exactly the same thing. And lastly, I have the source terms. So the DC part of the source is the 1. So I write down minus P naught times 1 times delta function in space. As for the frequency domain term, the only thing that's changed is I have an extra factor of A. So it's minus a fraction of the total power, P naught, and then a delta function. I can then close the brackets and say this is the entire equation. It's a bunch of DC terms and a bunch of AC terms. Now you're thinking, why did it break it up into 2 equations? Well, it's because the solution to the CW equation is exactly what we've already talked about in class. This is the solution for when you have a steadily glowing point source at the origin. It's just analyzing the steady aspect of the power source that we've got in this problem. So it's going to have the same solution that we've always seen. Let's write that out. So the solution to the CW equation is already known. And in the book, it's equation 10.3. And let's notice what it is. It's the DC term equals, and we're not deriving this here, we're just asserting it from what you've already seen. It's the power of the light source, 1 over 4 pi d. That d shows up in this location here. And then it's an exponential, e to the minus r, square root mu a, speed of light over d, all in the square root, over r. So that's the solution for the DC term. The powerful thing here is that the solution to the frequency domain equation is almost the same form as the CW expression. It's got the same delta function, all these other terms are parallel, only this term is different. So now we're going to play a little trick, a mathematical trick. We're going to take these two terms, which both have UAC in them, and we're going to notice that we can write those two terms together as minus mu A times 1. That would be this term. This is just minus mu A times 1. This term is minus mu A times negative I omega over Cn. That gives us the I omega here. So I'm just factoring out a mu A from both terms and rewriting them that way. And then I am left with a Cn and a UAC here. So what you'll notice is that the CW equation has minus mu A Cn times dc, and the frequency domain equation has minus this thing times Cn times UAC. If we define that to be what's called mu A star, this complex number that's simply a multiple of a complex number times mu A, I could immediately plug that in to this expression, and just where I see the mu A show up, I stick in mu A star. So that's exactly what we're going to do. So the UAC expression that we're seeking, that's going to be equal to, well, instead of P naught, we have A P naught, 1 over 4 pi d, none of that has changed. We didn't change the d here, we just changed this quantity mu A here. And then we have this exponential, e to the minus r times the square root of mu A star, which I'm not even going to write it as mu A star, I'm going to go ahead and write it out very explicitly. Times Cn over d, all still over r. This is the powerful thing that we then learn about frequency domain light, is that it behaves very similarly to the way CW point sources fall off with distance in an infinite tissue. These have this behavior in an infinite tissue, and the important thing is this top expression here. That's the only thing that's changed. So let's focus on that and think about how it changes things. So you'll notice what form it has. The form of that exponential, it's e to the minus r times a complex number. Whatever you do when you take the square root of this interior complex number, you get another complex number. So it's going to have the form, this exponential does, of e to the minus what I'll call k real times r times e to the I, what I'll call k imaginary times r. So this first term here is going to be amplitude decay. I'll write that amp decay. And this second term here, that's going to be phase accumulation. So this solution for the point source of amplitude modulated light, it decays versus distance just like the point source decays versus distance, the CW point source. But it also picks up a phase as it propagates over distance. That might remind you of some things you may have seen in optics classes. So I'll note for the record here that what you have to do now is solve for Kr and Ki. And we're not going to do that. So I'll write that we're going to do that elsewhere. But we have some logic on the limits here, because we know that if we oscillate the point source very, very slowly, or essentially not at all, if you oscillate it once per millennium, you should recover the DC results. So that means that the limit as omega goes to 0 of Kr should equal what we had up in the exponent for the DC term. So that would be square root mu A Cn over d, and the limit as omega goes to 0 of K imaginary should be 0. There's no phase existing. There's no meaning to phase if you're in a DC term. So there's therefore no imaginary term showing up here at all. So just to summarize all of this at the end, we have the total oscillation term has the following form. It's got a space-dependent part, which we call UAC of R, and it has this e to the minus I omega t, which notice we didn't write that here. This is just the spatially dependent part of the solution. So it's going to be equal to some fraction of the incident light source's maximum power, some recovered terms. I'll stick the R in the denominator down there, and then it's going to have the form of an exponential decay and a time varying phase that also varies with space, just like we're used to with other types of waves we see, where the phase of this field distribution varies as a function of what time it is and also where you are in the medium.